Hi everyone, welcome back to my video on control systems. In this video, I'm going to provide a general overview on what the compensator is about. Now let's start with the simplest form of what we can do with the system, or in general we refer it as our plant, GS. The plant can be anything that we want to control. That includes any systems such as electrical circuitry, or you have a mechanical damping systems, or if you are controlling an engine of a car or anything etc. Generally, we will perceive the plant here as something that we cannot change its dynamic, but we are trying to affect its output based on the input. If you can see here, basically the system will not be smart because the system cannot self-adjust. In order for you to have the output to be controllable, you have to manually inspect the output and then you have to change the input. Hence, what we normally do here is that we are going to add a controller, or what we say as the compensator. At the same time, we need to close the loop, hence forming our negative feedback system as we see always in the past. Here forms the systems that we will be using throughout the entire courses on the compensator design. Typically in the classical control theory, the CS will have three normal forms, which are the gain K and the lead lag controller, as well as the PID. Now let's talk about the actions and how would they improve the output of the system. The actions we normally look at three aspects. First, we will inspect their effect on the root locus. Next, we can look at their steady state, and they will potentially have some effects on the frequency domain, and the easiest way that we visualize is through Bode plot. For root locus, basically we can visualize the effect onto the transient. In the steady states, we'll be using the limit theorem to find out what will be the effect, and Bode plot will tell us about the performance in the frequency domain as well as its stability margin. Let's look at the gain first. Gain is basically just a simple multiplier of K. In the root locus, let's say this is the root locus of the system without any compensator, or we say it is an uncompensated system. Basically, by adjusting the value of the gain K, we are actually adjusting the closed loop pulse. And by meaning that the adjusting the closed loop pulse, which means that we are shifting the location of the closed loop pulse along the root locus, in the hope that we can reach some point where you exhibit a satisfactory transient response, because the location of the closed loop pulse in the S-plane will affect the transient. You will see that the closed loop pulse here has a tremendous effect on the transient performance that we normally use, which are the settling time, rise time, and maximum overshoot. We link the steady states error. Say here, we'll be using the steady state error for unit step response, which is A over 1 plus Kp. And our Kp, limit S goes to 0, C GS. And our C will be replaced by a gain K. You can obviously see from here that by adjusting the value of the gain K, you actually adjusting the value of Kp, and hence it will affect the steady state error. In general, the higher the value of the gain K, the lesser the steady state will be. But usually by increasing the value of the gain K, it will cause the system to be more unstable. In the Bode plot, a simple gain here will have no effect on the phase shift. That means the phase shift, if let's say this line is the original one, it will remain unchanged. However, for the magnitude, let's say this is the magnitude, by introducing additional gain K, it will actually shift up or shift down the magnitude plot by a magnitude of 20 log K. depending on what you want, you can actually adjust the value of the gain K to change the magnitude plot. Let's talk about lead lag now. We consider the simplest form to represent a lead lag. If we take a first order lead lag transfer function, we will have a gain K, and then we will have 1 0 Z, and we have 1 pole P. This is the simplest form that we can use for either lead or lag. If you wish to construct a lead lag, basically you have two layers of the zeros and poles. For the root locus, which affects its transient, the red line over here shows the root locus of the uncompensated system. And by introducing a lead lag or lag alone, we are actually adding the roots here. And it will affect the uncompensated root locus by shifting the shape of the root locus, which potentially to have something like that. By reshaping the root locus, which means that it is moving the new closed loop poles to a different location which is unrealizable using a simple gain K. And hence this normally result in an improvement on the transient response depending on the gain value that you choose. For steady states, we'll be using ESS equals to A over 1 plus KP as we used earlier. And this round, your KP will become S equals 0, K, S plus Z over S plus P times GS. The effect will be brought by the combination of K, Z, and P. And that will result into an improvement on the steady state response. And in the Bode plot, adding additional gain, zero, and poles will have an effect on the magnitude plot and also the phase plot. By introducing effects on the gain and also the phase plot as indicated over here, the lead lag controller can potentially improve the gain margin and phase margin of the system by lowering down the magnitude plot and also by increasing the phase plot at a certain point. And we will expect a similar result brought by the PID as well. You can see that the transfer function of the PID KP1 plus 1 over TIS plus TDS will result in a similar as in a lead lag because of the additional poles and zeros. Okay, I have provided an overview of the compensation techniques that we normally use in a classical control theory, and in the next video I'm going to introduce in specific on how do we calculate or determine the transfer function of the compensator with respect to a set of specification. Thank you very much for watching. Bye.